I appreciate the opportunity to come out here. It's my first chance to come to Michigan State. What I'll be talking about is kind of an overview of my perceptions of how I think sociologists and social scientists in general fit into interdisciplinary, or what I'm increasingly calling transdisciplinary projects, trying to understand a very particular set of problems. My set of problems have, what I'll talk about today, revolve around watershed management and hydrologic processes, water quality processes. Where in my neck of the woods, we're very interested in water quantity as well. And, oops, let me go back up. As an introduction, yeah, there'll be a lot of slides really fast. I've been working on this for about 20 years now, the issues of agricultural non-point source pollution. And when I look across that field, one of the things that I'm struck by is that there's been an enormous amount of science effort. There's been tremendous amounts of money spent developing models, developing understandings of how these systems are supposed to operate, trying to diagnose the water quality issues. But after those 4 decades of work, we basically are in a very similar situation we were in when we started, if not in some places a worse situation, which is an observation in some ways that the project seems to be failing. And when I talk to my colleagues who are not sociologists, what I understand from them is that really we understand the process. We know what's going on biophysically in their mind, and we have confidence that we know the solutions. We have a set of tools on the shelf that are good enough to solve the problem, and the problem is now the sociologist's problem, which is how do we get people to use the things. Now, I've got lots of responses to that, and today is one of my responses. So, to most people, it's a people problem. The human behaviors that cause the problems are the ones that have to be fixed. This is one of my favorite pictures from Wisconsin when there was a great fish kill in the one of the Great Lakes, and they didn't know what to do with all the fish. Well, the local farmers took them and loaded their manure spreaders and spread carp on their fields, which is just a wonderful image. It doesn't have that much to do with the talk, but I always try to use it if I can. So there are 2 roles that sociologists are usually given, and you're invited to be a salesperson, so you go out and your job is to try to tell people about these great things and convince them that there's a problem and what should be done, and get them to change their behavior using your magic sociology tools, whatever they might be. Or, more even frequently, you're a facilitator, which is really a front for being the person who has to talk to the people who are uncomfortable to talk to. So my hydrologic modeling colleagues don't like talking to farmers. It makes them nervous, and the sociologist supposedly, again, has special skills to go and interact with people that make scientists uncomfortable. Well, I reject these roles. I have for a long time. After a couple of tries, I realized this is not the right work to be doing, and it's not where my skills are best employed. And at first, I'd say I got excited about a 3rd role for social science. Now, believe it or not, we do research, and I think sociologists have a set of research tools and theories that are very valuable. And since these are, in fact, I agree, human problems, what we're talking about is the human dimension of the problem being the part we understand least, we've got some things that we can do. And so we address issues as basic as who are the farmers and what are they doing, but why do they do what they do, and what institutions shape what they do. And I argue that the best approach is to rethink the people problem in a way that my colleagues tend not to think about it. And this is the people problem being, how does all this social science insight and understanding, the rich understanding I have of the world of agriculture and conservation behavior, impact natural science? Like, where is the impact that I have on the kinds of ways they approach doing biophysical modeling? What is the role of a social scientist in an interdisciplinary project in doing studies of the dynamics of natural systems, so-called natural systems? So my hypothesis is it's not really a people problem, it's a science problem. The problem is the scientists have really not done very good science because they're modeling human systems without very much understanding of the human aspects of those systems. I mean, there are natural systems out there. They're really hard to find. We had a hydrologic laboratory proposal come out of Utah State, and I was on a teleconference where my colleagues at University of Utah were trying very hard to find a watershed in the Intermountain West that was not human impacted so they could do really good hydrology, and they couldn't find it. And my point was, the really good hydrology is the human impacted landscape. That is where you do it. That is where you have to understand it if it's going to be in the least bit interesting. So my hypothesis is that there's a fundamental constraint on science, which has been our inability to integrate human dimensions into what we might call real science or natural science, about how watersheds work. And this is where, in a nutshell, I'm talking about pushing boundaries, pushing social scientists to do work that we're not used to doing and getting our colleagues to let us. So let me give you a little history of how I think some of this has evolved and the kind of models I have in my head about how different models for collaboration. These models are all about what do social scientists understand and know about dynamics of systems, and how do we get involved in solving the systems. The system that I was brought up with is a system I call parallel play. It goes back to my wife, who was a Montessori teacher for many years, and so she saw nothing but 2-year-olds. And those 2-year-olds basically could share the space and even share some of the same toys, but they didn't play together. They played in parallel. And indeed, what I think happens much of the time with interdisciplinary projects, or I'll call them multidisciplinary projects, is parallel play. The natural scientists understand the natural science process about how the system operates. They develop ideas about where the problems come from and what the appropriate engineering or technical solutions are. They make recommendations, and then they hand it over to the social scientists to figure out how to get the policy right to induce the right behavior, or to promote and do that sort of salesmanship job. And the sociologists might give a little feedback saying, hey guys, it's not working, so there's a little feedback, and you hand it back to the natural science and engineering teams to recalibrate the tools, and we wait for them to drop upon us as social scientists so we can go sell them and hopefully get the product better. So you have your natural science moment and your social science moment. And so we get things like this. Now, this is the early days of natural science modeling, where you get black and white diagrams hand-drawn with squares and little arrows. This is a hydrologic system with all the important parts of the hydrologic system included, supposedly. This would be a modern version where now we have new software. We can make them color and have arrows in 3D. But it's basically all the important processes you'd have to understand if you were to go and study a watershed in many of the projects I've been working with. And the big question I have is, where's the human element of the system? It's very poorly represented, and it's usually often not existent. And this would be the sociologist then. We have our black and white diagrams. We haven't gotten 3D very often, and not color as often. But we would have, say, a microsociology's body of theory and work that talks about all the various things that are going on in these farmers' heads that constrain their behavior or make them do what they do and how they reflect and think. And it's good stuff. This is good stuff. Both of these are good things. When we do get 3D, this is like a macro sociology. What's the role of these various layers in society that structure behavior? But my question to these folks is sort of, where is the biophysical? So we've worked in parallel. We've got really good understandings of a supposedly idealized natural system and an idealized social system. Now, I'm not the first person to notice this. In fact, the more I read, the more I feel like my work is silly and old. In fact, I've discovered lots of stuff from the early 70s where this was a fervent discussion going on in the science community. But more recently, it's been discussed in this world of what we call coupled human-natural systems, which is a phrase NSF has used to fund certain body of research. And this is a recognition that, yes, indeed, natural system processes that we are interested in almost always are interesting because there's a human element, a human problem that's been generating things that need to be solved by society or addressed. And people do understand that our conventional disciplinary approaches to doing natural science are not well equipped to figure out what to do with human dimensions. So the incentive is there, the impulse is there to deal with this. And people have not brought social science in very systematically. So they recommend things like this. This is from the RFP for the Coupled Natural and Human Systems program. They want to understand something called interdisciplinary analysis of relevant system processes and the interactions among these systems at different scales. I just got an NSF with the team at Utah on the Water Sustainability and Climate program, looking at incorporating linkages and feedbacks between all these different things, which include atmosphere, oceans, and social processes. So the idea is very good. The impulse is to fix this. What I see on these projects is that the typical role of the social science is still to have an area of expertise that includes these things. We understand the behavior part of the program. We understand the logic of behavior and maybe some ideas about the exogenous drivers, markets and policies and law and culture. And we've got what I would call sort of a linked systems model now, where we are working together. We're coupling human and natural systems. But the sociologists or the social scientists writ large are still up in these boxes. This is where they live. This is where their expertise is. This is what they are called upon to do. And so we do it, and we do it well. I mean, I don't want to convey that this is not good work or important work. But when we do this, we also have people who are doing biophysical studies still, whose expertise and authority is understanding that process and trying to understand the impact of biophysical processes as they relate to behaviors that are clearly human and their impacts on water quality. And we still rely pretty much on that natural science community and engineering community to generate the solutions, the best management practices. Everyone's comfortable with BMPs. I did not define my acronym, best management practice. And there's still the feedback loop where when we understand adoption patterns and so forth, there's some tweaking of the markets and the policies and the programs. And this is better, but I still think that there's a very clear difference in the natural science moment and the social science moment. So we've linked our parallel players so that we hand things across a line that the social scientists will communicate, and there's a bit of feedback. But they're certainly playing in their own sandboxes still. Let me back up and give you a little background about a program that got me thinking about this. And it was a program that I got involved with 5 years ago to do a watershed study under the USDA's Conservation Effects Assessment Program, the SEEP program. The idea of that program is to try to find out in some magical way, using science, whether or not the things we promote as conservation practices have actually had the impacts we expect them to have at the watershed scale. And it was Congress saying we've spent hundreds of millions of dollars, billions of dollars really, on trying to promote behavior, and do we know if the water is clean yet, and which practices are working? So it came from an interesting impulse. But the idea is pretty straightforward. They fund teams of scientists, interdisciplinary teams, to go into a watershed and somehow answer the question, did the conservation practices change water quality in some meaningful way? Most projects around the country have really struggled, though, to get any real data on conservation behavior at the watershed scale. They've relied on official records, they've relied on remote sensing. It turns out that many conservation behaviors are not easily remote sensed, like nutrient management planning and fertilization practices. But what happened is most of my colleagues, as I've attended these national meetings, have ended up just simulating hypothetical behavior because they don't have real behavior, so they have these models that have human dimensions in which the human dimensions are optimizing models trying to find the right arrangement of practices on the landscape that's economically efficient and environmentally high impact. So it's not answering the question, does the way it actually happens in the field clean up the water, but if you were to do it right, this is the way to get, so they've got human dimensions, but they're all simulated perfect human beings. And then they hand it to us and say, figure out how to make them do it this way, right? Do it here, not there, is the new question. So in my project, our little SEEP project, I actually got quite involved, because I bought into this linked system idea, in getting real data on behavior. And we spent a lot of time and money, and my students spent a lot of hours out in NRCS offices and interviewing the people who received conservation grants to find out what happened and what they did and where they did it in inordinate detail. So I was obsessing about getting the human behavior recorded in detail. And my expectation was I would give this data to my colleagues and they would put it in their model. And they'd be able to use real data this time to be able to project what those real behaviors, as they were imperfect and spatially and temporally specific, whether those are linked to real data on water quality. And we'd understand whether variability in behavior within the watershed can be linked to variability in measurements of water quality. What I found is that they can't do that. They don't know how to take real data on behavior, and because the models were built with a very different set of assumptions. And those set of assumptions are that behavior is a certain kind of thing that's been parameterized rather than something that you figure out by gathering information and inducing it later. And in particular, the hydrologic models that are used for water quality modeling are incredibly detailed when it comes to biophysical variables, but have very few proxies for the human dimension, and they typically are treated as very crude land use categories. So the category of corn production has a coefficient, has a set of assumptions as to what corn production is. It's a thing, it's a single thing. And that struck me as odd. Because I had all these data to suggest that people were managing corn in all these different interesting ways, and so they couldn't allow me to put in 10 different ways you can raise corn. I'm going to keep going here. So the biggest remaining problems, I think, having had that experience in the literature and in the practice of doing this kind of watershed interdisciplinary work, is to actually do a better job of incorporating the human elements of systems within the work that's always been the terrain of natural and biophysical science. And so it's a challenging, boundary-pushing endeavor because it's not something that people have been comfortable doing. And how it is done is still being figured out. As I point out in a lot of my interactions with them, the level of detail and nuance we have in terms of soils down now to the half-meter pixel length and topography and climate simulations that are incredibly refined versus the level of detail we have on the human dimensions of these systems in the models is night and day. It's orders of magnitude different. And so that's how I get through to them to say, well, it's not that it's too much work, it's just different too much work, because you've been doing too much work, probably too much detail on the biophysical side, and we've been underinvesting in getting real information about what's out there on the landscape on the social side. And it's hard and it's expensive, but maybe a bigger share of the budget could be spent on it. Okay, and the reason is, I think, that they don't know what to do with the data, and the data aren't easily available from public or familiar sources. You need to think about how to gather those data. All right. So I'm going to argue that we need to go in some new directions. We need to improve what kinds of data we have on human elements of these systems, and in particular we need to understand and figure out how to represent diversity. So we don't treat human behavior as a relatively simplified thing, but we actually explore ways in which that diversity tells us a great deal about the functioning of these systems, because I think there's a lot of value in that. So like I said, we got an NSF grant, and one of the reasons we got the NSF grant might be that we had a really cool graphic. I think it's a really cool graphic. And this graphic came out of some really long meetings and lots of iterations, and it was an aha moment for me. This is a watershed to me. Okay, the watershed is a thing that has at least three kinds of things that comprise it. The watershed is a geophysical phenomenon. It does have topography, it has a climate regime, it has precipitation, it has certain aquatic, or hydrologic functions between groundwater and surface water. It's an ecological system. It has all these above ground ecological systems that are operating, but it's also a human system. The watershed is a human system. It's not something that the humans live in, but you think of the watershed as quintessentially both geophysical, human, and ecological at the same time. And some of the challenge is to try to understand that system as an integrated whole, with the human dimensions being just as interrelated as we typically do within the geophysical and the ecological. And so we focus on some of these sort of boundary arrows in our proposal about how one does that kind of research. You don't do human systems research, you do human nexus with geophysical, and you do human nexus with ecological. And there are macro contexts. We've got climate people who are big macro geoscience. We've got some macro ideas about regional ecological dynamics. And there are macro social science pieces that are an important part of the thing. But the key part is that middle circle where we reject the idea that there's a separate social science moment to understand how a watershed process works. That just as important as the soils and the bedrock and the precipitation regime is understanding the human dimension of that watershed. And I've got some colleagues that think they're going to go along with this. We'll see how it works, because we're just launching into doing the actual work, but I think we're getting along. Some people fell off the cart. They began to talk about this, and it wasn't familiar, and it was uncomfortable, and it was difficult to keep people on the team, but those who stuck it out are buying into it for now. So how do you do this? There are three questions that I'm going to talk a little bit more about. that seem like obvious questions, but I think as you unpack them, they get really interesting. One question is, what is the BMP? In fact, what do we assume we're talking about when we talk about the impact of a best management practice? And this is something I've thought about for a long time. The second are some problems with representing and trying to simulate the net impacts of best management practices. And then the final is some ideas about how we actually go out and account for real infrastructure and behavior. Okay, so there are definitions of BMPs. There's a guide, in fact, that defines what a 313 is, and it's technical, and it gives you an idea of what it's supposed to be and how it's supposed to be used. And generally speaking, when we operationalize BMPs in the modeling world, we use those sort of standard engineering definitions about its specifications and its performance. So we know that from research on land-grant universities that a waste management plan should reduce your phosphorus by a certain percentage, because some studies were done to suggest that the perfect plan on some idealized situation could do that. But empirical research I've done for all my career suggests that it's really problematic to assume that a plan is a plan, or that even a fairly well-recognized tool is the same tool in every instance. And there are big questions I have about the problems that creep into our science if we make that assumptions. And let me give you a couple examples. One is a waste storage facility, the 313 code. A waste storage facility is, if I were to read, an impoundment made by constructing an embankment or excavating a pit, and it's used basically to store your manure to allow you to manage it differently. But the impact of a waste management storage structure on the environment is not by building the storage structure typically. It's by facilitating farmers to be able to store their manure for extended periods of time and incorporate that manure during better windows when the crops can use it. So there's this whole suite of behaviors that go with the installation of a structure that make it work, without which it really makes very little difference in the world. So it's part of an overall planned waste management system. The realities of waste storage are that even you go look at the kinds of structures that are built, there are cement ones and big ones and small ones and clay ones and deep ones and big enough ones and not big enough ones. And so in our watershed, this was one of the big management practices that was consumed a lot of the resources, but what was actually done was as diverse. We had one waste storage facility that was a straight line cement wall against which you could push your tractor. So it's not capturing very much, because if it were to build up much, it fairly easily got, and you could see it was getting around the edges pretty regularly. But it was a version of a 313 that had we not gone in the field, we could have modeled as the same 313 anyone else had. And that the impacts of these structures is going to depend entirely on the decisions farmers make about manure handling and their nutrient management planning. And research I did in Wisconsin suggests that even when you have a structure, your behavior won't necessarily change. We had a high percentage of people who'd been paid to build these structures who continue, for example, to spread their manure on a daily basis, which is exactly what these structures were designed to prevent you from doing, or to allow you not to have to do. But for a lot of other reasons, this still made sense to a large fraction of Wisconsin farmers. And we know from a lot of research that farmers are unable to access their fields in a sort of optimal way for logistical constraints, labor constraints, weather constraints, and so they spread their manure in ways that are not taking advantage of all the things recommended in their nutrient management plans. Another example is my favorite story. I had a master's student write a thesis on total mixed ration machinery, and it's a well understood feeding machinery technology in the dairy industry, which is designed to basically grind up all the feed into a homogeneous mass so the cows can't pick through and eat what they want. And it's designed to allow you to feed separate classes of cows at different stages of lactation, a specialized diet, and there's a great deal of engineering, and to find out what the TMR is, we had to read the sort of engineered guides and publications that designed these things. And what we found is that when we went out and found TMR users, and we got a random sample of farmers, and we went back to those who reported TMR use, that more than half of the sample was not using the TMR correctly in any reasonable way based on how the TMR was designed. We had people who had TMRs who didn't use them. We had people who used TMRs as nothing more than a labor-saving device that allowed them to just drive down and feed their cattle because the TMR would spit the feed out the side, but they weren't balancing rations, they weren't paying attention to what they were feeding, they certainly didn't separate feeding by lactation group. So the existence of a TMR became this very complex object, and we argue that it sort of deconstructs the idea of a BMP being a tool or a single thing. Another question is, what is the impact of a BMP? And all of these models that I work with right now, I'm trying to understand and adapt, have built-in coefficients about the percentage impact of a given type of practice. So the storage has an impact, TMR might have an impact. And that assumption of a standard impact depends on BMPs actually being a certain thing, which I've already problematized, that they be implemented and used, which I will problematize more, and that there be consistent baseline conditions on which the BMPs are placed, so that everybody who didn't use the BMP manages their fields this way, and then the BMP will be able to change their behavior in some predictable fashion. In fact, there's very little study, to go on to the implementation question, of whether BMPs are actually implemented, and more often than not, whether they're, or less often, whether they're still there after the year in which you install them. There's no money, there's very little effort to go and keep track of things for the long run. Well, I did, because we, as part of our SEAT project, proposed going in and assessing a project that had been done really in the 90s and early 2000s. And so we show up, we were both documenting actual behavior, but also doing sort of a long-run implementation and maintenance study. And we, through our field interviews, were able to formalize an assessment of hundreds of practices as to whether they were implemented successfully and still used. What we found is that probably with an average of about an 8-year window, about 80% of the practices had been originally successfully installed. That's a pretty large fraction that never actually got put on the ground, but there's lots of reasons. I don't have time to go into them as to why. But the reality is that the records of practices were not consistent with the actual implementation. And even at the farm level, this wasn't because there were a few farms that failed. It was pretty normal on farms to not get everything in. So only less than a third of the farms got all their practices in, which means the overwhelming majority had at least some that didn't happen. This is pretty common. And I think as I've talked to people around the country, this is not unusual. It's not just Utah farmers. In fact, I know from Wisconsin work this was true in Wisconsin. The maintenance question is even more interesting. Okay, so that was implementation back in 1996. Did you actually do the thing in your contract? And how'd it go? Did the trees die right away? Did they stick? We found that 20% of the implemented practices are gone. So you had 80% implementation, and then you have 20% of them no longer being used. They're not still there. And when you do the simple math, you find out that about a third of the originally contracted practices are not on the landscape having any impact on water quality. And one of the big reasons they're not being maintained is that people got out of farming or changed the structure of their agriculture. So they either grew their farm or shrank their farm, but the practices were no longer even relevant to what they'd been originally designed to do, and so they were rationally not using these practices. But as a simulation and modeling exercise, that raises some really big challenges. All right, and just to give you a quick feel, the green bars are the percent implemented, the red the percent of those implemented that are still there, sorry, the blue, and the red is the multiplication of those two. And you can see that some kinds of practices, like management practices, have a much lower success rate than practices that are hard structures. But even hard structures had about an 80% survival rate at the end of the day. Less than half of the management practices were still tangibly being done. So some other problems with pre-BMP conditions is that there's great complexity in the pre-existing situation that farmers do. This is a graph from a colleague of mine at Wisconsin about estimated rates of nitrogen application on fields, and the little line shows you basically the percent of farmers that use different rates of nitrogen application. Well, that little blip in the middle is the recommended rates, but what you see in the distribution is it's incredibly variable, and there's some people that are far out on the tail that apply nitrogen well outside of recommended practices. But in all the modeling work I've ever seen, people pretty much use recommended practices as their surrogate for what's happening out there on the landscape instead of gathering data on real application. The same is true for phosphorus. Another study I did was looking at dietary practices. The problem was that for those of you who study phosphorus, farmers feed sometimes excess phosphorus, and so the magic bullet 5, 8 years ago was, let's get them to feed less phosphorus, maybe by implementing different kinds of technology, but basically get the level of phosphorus down in the diet so they'll excrete less surplus phosphorus. And the assumption by all of the experts, and I was working with really some of the key experts in Wisconsin that do this dietary nutritional work with dairy farmers, was that farmers feed 0.5% phosphorus. And the reason they argued that it was 0.5% phosphorus, or they knew this, was because they knew a lot of experts that were involved in counseling the really good farmers, and they were all recommending 0.5% phosphorus, even though the National Research Council only recommends 0.38% phosphorus. But they talked to guys who worked with 10,000 cow dairies, and they knew really well that that was what everyone was still doing, and this was potentially an area of great improvement, because NRC thinks we can feed less. That would make a big difference in excretable phosphorus. What we found when we went out to a random sample of farms and collected what they're actually feeding and did analysis in the lab was that, in fact, the assumption of 0.5% phosphorus was flat out wrong. There's a wide range of behavior, but not only that, people are feeding 0.4% phosphorus already. So this was the distribution of a random sample of diets, and the original assumption is 5, basically. The actual is 4, but you also have these huge tails and great diversity. So to model phosphorus, as we had actually done as a 0.5% diet, and what that means in terms of the amount of phosphorus getting out of the cows and into the system, you at least want to start with the right mean, but maybe incorporate an understanding of the diversity. The final example I have, I'll just give you 2 versions. This is the amount of percent of farms that can get rid of their manure nutrients given their land base with 2 assumptions. On the left is if they follow their recommended nutrient management plan, 62% of Wisconsin dairy farms are able to get rid of all of their nitrogen and phosphorus. 4.6% can't. That's a simple way to view this graph. When we actually go out and look at what percentage of their fields they do spread manure on, we find that 71% of Wisconsin dairy farmers are unable to adequately get rid of their nutrients. They're spreading too much on too little land, and only 5% are able to do it successfully. So the real behavior totally changes the interpretation of what's happening on the landscape. So, most BMP impacts have been modeled as textbook, standard coefficient, simple practices, human behaviors that are not problematic, and placed on top of an understanding of the universe that's a standardized starting point. So what do we do better? I will argue that we need to collect more data. And I know that's a fairly banal thing to say, but in fact, I do think it's a big problem that we haven't invested very deeply in getting good information, contemporary information, specific information about the human dimensions of watersheds where we're trying to do this kind of modeling work. And like I said earlier on, we just got to spend the money. We got to invest in actually getting good data. It's not rocket science, really, but it does mean that we would understand the human dimensions in some important ways. Now, the kinds of data include things like the built infrastructure. Our NSF project is about water management, and it grew out of the fact that in the Little Bear River, where we did our SEEP project, all of the water quality monitoring stations were in the river. Makes sense. And we had these hydrologic models that modeled how water filters through this landscape. We were out, got the grant, we go in the field, the very first field tour, we're standing on the edge of the Little Bear River, and there's no water in the Little Bear River. Because in Utah, as is true throughout the West, for 5 months out of the year, the entire river is diverted through irrigation systems. Not a single model of that system has ever included irrigation diversions, canals, how that water is getting back into the water, and no one's ever thought, and I'm still struggling to get this to happen, to measure water quality in the human infrastructure. You go ahead and put your monitoring stations where the water is actually flowing for almost half of the year. So just getting good information about the built infrastructure that moves water around is, to me, a major thing. Now, I've since learned that this is a big deal in this region as well, with all the tile drainage systems, all the manipulations of how humans have changed fundamental hydrologic processes. It would be silly to not pay attention to that. There's non-built infrastructure, or non-ag built infrastructure, that also affects water that has to be represented in these. And it just so happens that water quality landscape modelers seem to be naive, not just about agricultural behavior, but ignorant about all the other non-agricultural activities that are going on, at least the people I've been lucky enough or unlucky enough to be working with. So measuring a lot of those sort of developments and their impacts on the system is important. Like I say, we should document actual behavior. not imaginary behavior, and look not just at averages, but at distributions, and parameterize and find ways to use that in our models. And then we got to go beyond description. This is my easy slide just saying that, of course, we are sophisticated social scientists. We understand that it's not just a question of documentation, but trying to understand the dynamics of behavior and the motivations of behavior. I'm not talking much about that today because I presume we'll keep doing that. I will say that the experiences I have suggest that as we do represent human behavior and the processes behind human behavior, we definitely want to go beyond economics. And this is maybe not a shocker from a sociologist, but that clearly the models of human behavior that we want are going to be more than rational economic activity, because I've never found farmers in my work that best describes their conservation behavior, that they're making only economic decisions. And then I have some other issues up there, most notably that we should probably at least think about farmers not as an entity, but as a set of clustered entities that maybe have some simplifications in them, but that we can think of different categories of farmers and landowners and decision makers in a watershed, not just farmers. All right, is this too much to do? Probably. But this was the map that was in the New York Times a while ago when I was preparing a presentation, so I bring it out. But this is all the great connections between all the different people in Iraq. I think it's Iraq or Afghanistan. But I do think we can move forward. So how do we do it? The first stage is you bring human dimensions right inside the biophysical model. You have to learn some things about hydrologic modeling. You have to understand some things about riparian ecology. You have to learn some things about the dynamics of nutrients and nutrient systems, and still be a social scientist or a human dimensions person to be able to identify what elements of the human system that you know about are actually relevant for these biophysical processes. And I'm making a living now in annoying my colleagues by interjecting myself into the design of their work. So I help decide where the monitors are going to go in our instrumented watershed. I help make them find the canals and GIS them and put them all into the system and figure out what they're going to mean. I make them try to understand how irrigation behavior is affecting hydrologic processes. And that's hard work. If we do it well, I think it begins to open the door to a better kind of science, a better representation of what's going on. And the key, as I've said at the title, is to blur these boundaries. To go back to this model, we really want to figure out how to do a single science project that's human and natural inside that watershed, to figure it out all simultaneously as opposed to as a stepwise linked progression. Now, there are some things we can do, we can use. As I said, the more I know what I do and I know how I do it, but I'm beginning to find the language to describe how it's been referred to by other people. And one of the areas is to think of this as a version of either interdisciplinary or transdisciplinary research. It's not a new topic, but it's a hot topic, and these are all new books that I've been buying and trying to read. On the airplane on the way out, I was reading one of them. And what I'm gaining in my little foray into the world of science, of transdisciplinary science studies, is that there are at least these three steps that most people understand. The step from disciplinary to multidisciplinary, I think as best represented by the parallel play model. The step from multi to interdisciplinary, where you do somehow have to interact with other sciences and other disciplines. And then this third step that's kind of controversial and less well understood, of inter to transdisciplinary, where we, in theory, by some people's models, blur those boundaries. We no longer think quintessentially about the disciplines having to just understand one another, but they're either problem-centered or transcending disciplines. And this is a graph that I found very useful. I'm trying to use it with my own research team to get them to understand what this means. These would be stages of moving from from disciplinary to transdisciplinary. And in one case, every discipline, there's a dominant discipline. It's not sociology usually. There'll be everyone's an expert in their discipline, and they bring that expertise, and everyone defers to them to do their part of the project. And people generally work more of an individual capacity with a shared budget and shared F&A. Now, the middle, we get sort of people working in parallel play or more of a linked system, but there's still, while coordination, there's still some expertise that changes. The kind of deep integration is when Doug gets to get involved in the design of the ecological side of the experiments and how we instrument and how we interpret and how we think about the problem, as much as just the people who bring that to the table. Transdisciplinary is also really important because it brings stakeholders in some people's minds to the table. And I think the role of stakeholders parallels these three steps. Let me give you an example. The first step is treating the stakeholders like your audience, like I started this talk with, where our job is to go out and teach them about the things that they should be doing, or to make them concerned about something we think they should be concerned about. And if we don't engage them, then we can't solve problems. So our stakeholders, as we've done our good work, find out what the problems are an audience. I think at the intermediate stage, we see our stakeholders as potential informants. We know that they know some things, we want to gather it, we're going to bring it back home, and we're going to use it to kind of better our work. The final stage is the stakeholders are actually invited to be involved in the actual science. The stakeholders help us define the research questions. They help evaluate the quality of the modeling, and they identify things we wouldn't have noticed. So we break down the boundaries between the scientists and those outside of science, and we get them involved in these kinds of things. So they actually have a role from the front end through the back end of integrated research. Now, all is not lost. There's some efficiencies, and I'll just give you two quick examples. Pete Nowak, a guy I worked with for a while at Wisconsin, who I still interact with a great deal, has been promoting the idea of disproportionality. The idea of disproportionality is that it's not really that all parts of the landscape are important or equally important in understanding a process. And it's also not true that all behavior is important. So we don't go out and have to measure every behavior by every person everywhere. But we can be very targeted in terms of understanding where the nodes of action are in a system. The graphic he likes to show is this one, where we have that disproportionate tail on fertilization practices, and we know from landscape modeling that there are certain critical areas in landscapes that deliver most of the phosphorus to the water, for example. Well, let's overlay those two. Let's find out which farmers are over-applying phosphorus on landscapes that are dangerous, and let's work with that part of the landscape. Let's really understand dynamics of that part of the system, and those people, and those physical, and those ecological outcomes. And so you focus in on that intersection of vulnerable landscape and inappropriate behavior. The other tool I think we have that makes this tractable is that I am enamored, although I can say I'm enamored without having tried to do it, with this emergent idea of doing participatory modeling. What participatory modeling essentially is going into a watershed and saying, stage one, we think we know some things about how the system works. We're going to try to model it. Stage two is we bring that model as a starting point for a conversation with a population to say, what did we miss? This is our silly little academic ivory tower model. Probably doesn't represent some things well, but it suggests that this is what's going on. What do you think is going on in this watershed that is different, that we haven't captured well? And now that I've peeked under the hood of these models, I can tell you there's a lot of problems with the models, a lot of really simplifying assumptions that even someone like me would notice with what I understand about how the world works. And so I think that there's great opportunity if we're willing to open our models and explain in an engaged relationship with stakeholders or real people in the world what we're doing, that we might actually get some very important feedback. So this complexity of locality idea that's part of the transdisciplinary literature is that expert-driven processes only can take you so far, that building something into the science itself that is a way to engage local feedback and information in substantive ways, in the science itself, not just in the implementation of the implications of science, can give you different kinds of outcomes. And the benefits, they say, and I'm selling people on this, and we're going to try to do it, is that we get better science. So our models are better. They should be. If they were wrong, if we didn't have the irrigation canals modeled and that's where the water goes, well, by God, it was a dumb model. And we ought to get a better model that really represents the dynamics of water and nutrients. And we can get feedback about unanticipated things that we might not know. Secondly, I think the modeling exercise as part of this social project to deal with problems like water quality become more impactful, because if they're along for the ride, the problem of convincing them about what's going on in the watershed is I wouldn't say solved, but you're pretty far down the road if they were part of the diagnosis of the issue. And they had a chance to kick the modelers really hard and push back and adapt and gain some ownership in what that model is saying and doing. There's a learning process. Is this easy? No. Is it cheap? I don't think so. But is it going to probably lead to both better science and better outcomes? I think it could. And then, as I say at the end, it also becomes potentially interaction in a relationship that could lead to new science, new questions, and adaptive management. So, I made it to there. I threw a lot of slides at you.